Hello all, I welcome you all for today's lecture on Operational Amplifier. Myself, Dr. Muralidharan, Associate Professor, Department of Electronics and Communication Engineering, KPR Institute of Engineering and Technology, Coimbatore. So if we consider the operational amplifier, it has two input terminals and one output terminal. The terminal with the negative sign is called as an inverting input terminal. Terminal with the positive sign is called as non-inverting input terminal. There are three types of packages available. One is metal can package, another one is dual line package, flat package or the flat pack. Op-amp packages may contain single, dual or quad op-amps. Typically, packages have 8 terminals, 10 terminals and 14 terminals. The widely used operational amplifier is MUA741, which is a single op-amp. Now let us look on to the operational amplifier symbol as well as pin diagram. When you look at the screen, the operational amplifier symbol is represented with the 5 terminals. One is non-inverting terminal, another one is inverting terminal. These two are going to act as the input for the operational amplifier. And another one is, as we discussed, the output terminal. And the remaining two are positive supply and the negative supply. These supplies are most important for operational amplifier. And when you look at the pin diagram, it is a MUA741 operational amplifier. It consists of 8 terminals. First pin is offset terminal, second pin is inverting terminal, third pin is non-inverting terminal, and fourth pin is negative power supply, fifth pin is offset terminal, sixth is your output terminal, seventh is your plus VCC, and eighth is not connected. Now let's look into ideal operational amplifier characteristics. First one is the open loop voltage gain, which is going to be infinity, and this is most important characteristics of the operational amplifier. The next one is your input impedance, which is represented with Ri, which is also equal to infinity. Third one is your output impedance, which is represented using R0. It is going to be equal to 0. Fourth one is the bandwidth, and the bandwidth also has to be infinity. And the last one is zero offset. That means if V naught is equal to 0, when both your inputs V1 and V2 equal to 0, when input voltage is 0, that is what the meaning of your zero offset. Now let us move on to the operational amplifier configuration. Basically, it was classified into inverting amplifier and non-inverting amplifier. Now let us look on to the inverting amplifier. When you look at the diagram, it was connected in inverting amplifier configuration. The input VA is connected to the inverting terminal via resistor R1, and the output of the operational amplifier is connected to the input with the feedback resistance or RF. At the same time, if you look at the non-inverting terminal, it was grounded. When you look at the diagram, the input current I1 is flowing from Vi to the node of A, and the same current will be transferred to the output V0. Since your input terminals of the operational amplifier does not consume any current, the current flowing through your input terminal has to be 0. The same is applied for the non-inverting terminal also. And one more thing is the non-inverting terminal is connected to ground, so the potential available at that node will be 0. So the basic mode of an operational amplifier will have a difference between the two input terminal has to be 0. So the voltage available at the node A also will be 0. We have seen the basic construction of the inverting amplifier. Now let us move on with the analysis of the inverting amplifier. For simplicity, let us assume an ideal op-amp. As Vd is equal to 0, which is your difference potential between your input terminals, will be equal to 0. Node A is at the ground potential, and the current I1 through R1 is equal to I1 is equal to Va by R1. Also, since op-amp draws no current, all the current flowing through the R1 must flow through RF. So the nodal equation of the node A, or we can say Kirchhoff's current law, is equal to Va minus Va divided by R1, which is equal to Va minus V0 divided by RF, where Va is the voltage available at the node A. Since the node A is at the virtual ground, Va will be equal to 0. Therefore, the above equation is modified as V0 by Va is equal to minus Rf by R1, which is equal to gain of your inverting amplifier. Now let's move on to the non-inverting amplifier configuration. When you look at the diagram, the input was connected to the non-inverting terminal. At the same time, your inverting terminal, which was connected to the R1, is grounded. So this is the basic difference you can identify from the inverting amplifier as well as non-inverting amplifier. So here your input source VA is connected directly with your non-inverting terminal, and your inverting terminal which was connected with the R1 is grounded. The feedback resistance exists same as the path. Now let us consider VA is supplying a voltage source. So the same voltage will be available at the node A, because we know that the difference of the potential between your input terminal equal to same or 0. Let's move on with the analysis part of your non-inverting amplifier. As we know, Vd is equal to 0. The voltage at node A is Vi, same as the input voltage applied at the non-inverting input terminal. When we are applying the Kirchhoff's current law at the node A, the equation will be V0 minus Vi divided by Rf, which is equal to Vi minus 0 divided by R1. If we simplify that one, so we can write the equation in V0 by Rf minus Vi by Rf, which is equal to Vi by R1. Further, we are classifying into the input and output voltages. The equation will be a V0 by Rf, which is equal to Vi by R1 plus Vi by Rf. Further, if you are taking input voltage on the right hand side to the outside, so it will be rewritten as V0 by Rf is equal to Vi into 1 by R1 plus 1 by Rf. If we simplify this equation further, for gain value, gain will be equal to V0 by Vi. The output equation will be modified as 1 plus Rf by R1. Now let's discuss some operational amplifier applications. First, let us consider the adder circuit, or you can say it is a summer circuit, which was connected in the inverting mode. When you look at the diagram, there are three sources were connected to your input terminal with resistance Rin. All are going to be equal. At the same time, you have the feedback resistance Rf, and your non-inverting terminal is connected to the ground, where it will be giving the zero potential. When you look at the V1, which was supplying I1 current through Rin, when you consider the V2 source, it is supplying the current of I2 through the Rin. When you consider the V3, it is supplying current of I3 through the Rin. So all your input resistance were considered to be equal. At the same time, when you look at the virtual H summing point, which is mentioned as X in this diagram, will be equal to 0. Since the input terminal potential has to be 0, so the non-inverting terminal is connected to 0 potential. So obviously your voltage at the X node will be also equal to 0. At the same time, the current flowing through the feedback path is IF, which was mentioned in your circuit. Let's move on with the analysis part of this adder or summer circuit, which was connected in the inverting mode. So here we need to find what is the Vout with respect to inputs given in the circuit. So we are going to do the nodal analysis equation with the help of Kirchhoff's current law at the node of X, which will be given as V1 minus 0 divided by Rin plus V2 minus 0 divided by Rin plus V3 minus 0 divided by Rin, which will be equal to 0 minus Vout by Rf. Here we need to find Vout. So we are rearranging the equation. So this will be equal to minus Vout by Rf, which will be equal to V1 by Rin plus V2 by Rin plus V3 by Rin. So we need to find only Vout. So we are bringing the remaining terms to the other side. So Vout will be equal to minus Rf into V1 by Rin plus V2 by Rin plus V3 by Rin. Now we are bringing Rf to the inside of the bracket. So this will be equal to Vout equal to minus Rf by Rin V1 plus Rf by Rin V2 plus Rf by Rin into V3. So this is the output which was calculated for the summer circuit which was given here. Further, we need to simplify to get the addition of the input terminals. So from the above equation, if you want to act this as an adder or a summing amplifier, let us consider Rin is equal to R. Then your output will be modified as Vout will be equal to minus V1 plus V2 plus V3. So this will give you the addition of all the three input signal, but the negative sign was showing that all your inputs were connected to the inverting terminal. If the same circuit, if you want to act it as an averaging amplifier, that is also possible if you consider the equation of Rin equal to 3 into Rf. Then your output equation will be modified as Vout will be equal to minus of V1 plus V2 plus V3 divided by 3. So in general, if you want to act your adder circuit as an averaging amplifier, you have to consider your input resistance equal to n times of Rf, where your n is going to play as the number of inputs of the circuit. Now let us move on to the adder summer circuit, which was connected to the non-inverting mode of configuration. Let us consider all our inputs are fed into the non-inverting terminal through the sources V1, V2 and V3. All your resistance, corresponding resistance are R1, R2 and R3. At the same time, your inverting terminal is connected to the ground through the resistance R, and you have the feedback resistance of Rf. Now let us consider the analysis of the non-inverting mode of adder circuit. The nodal equation is applied at the node A, which will be equal to V1 minus VA divided by R1 plus V2 minus VA divided by R2 plus V3 minus VA divided by R3, which will be equal to 0. So from out of this equation, if you are simplifying and you want to find out the nodal voltage of VA, so that can be applied at the inverting mode. So VA will be equal to the numerator will be equal to V1 by R1 plus V2 by R2 plus V3 by R3. The denominator will be 1 by R1 plus 1 by R2 plus 1 by R3. Now let us consider the output path for the analysis. If you are applying the Kirchhoff's current law for the output path, the equation will be V0 minus VA divided by RF equal to VA minus 0 divided by R1. So we need to simplify this equation so that we can substitute the value of VA in this equation, so we can get the relationship between your V0 and VA. So after the simplification, we will get V0 will be equal to 1 plus RF by R into VA. We need to substitute the value of VA which was defined or calculated in the previous equation. So VA will be equal to, the numerator will be V1 by R1 plus V2 by R2 plus V3 by R3. The denominator is 1 by R1 plus 1 by R2 plus 1 by R3. So this value we need to substitute in this equation. So the output equation V0 will be equal to 1 plus RF by R into the value of VA we are substituted here. Now let us consider the value of R1 and R3 will be equal to RF by 2. So the above equation will be modified and we will get the equation of V0 will be equal to V1 plus V2 plus V3. Now let us consider another operational amplifier application, which is your subtractor. In the subtractor, we are going to feed two inputs, but both the inputs are not fed into the single terminal. Both the inputs are connected to the inverting as well as non-inverting. When you look at the diagram, V1 was connected to the negative terminal, V2 was connected to the positive terminal. So resistance also R1, it was equal resistance was connected to both your inputs, and you have the R2 as the feedback resistance at the terminal, V3 is maintained in that node. Now let's move on to the analysis of the non-inverting node. We are going to apply the nodal equation with the help of Kirchhoff's current law. The equation will be equal to V2 minus V3 divided by R1, which will be equal to V3 minus 0 divided by R2. So here we need to find the relation between the V2 and V3. So on your left hand part, it was redefined and rewritten as V2 by R1 minus V3 by R1, which will be equal to V3 by R2. So we will keep V2 at the answer another side and V3 on the another side. So now the equation is V2 by R1 equal to V3 by R1 plus V3 by R2. So again, you are taking V3 on the right hand side outside. So it will be equal to V2 by R1 equal to V3 into 1 by R1 plus 1 by R2. So again, taking the LCM and we are predefining, the V3 will be equal to V2 into R2 divided by R1 plus R2. Now let us consider the nodal equation at the inverting node. So the equation will be V1 minus V3 divided by R1 equal to V3 minus V0 divided by R2. Again, we need to segregate this one in terms of V1, V3 and V0. So the left hand side will be rewritten as V1 by R1 minus V3 by R1 equal to V3 by R2 minus V0 by R2. So after bringing all your input terminals one side, the V0 will be equal to V1 by R1 minus V3 by R1 minus V3 by R2 will be equal to minus V0 by R2. Again, after simplifying, the final equation will be V1 by R1 minus V3 R1 plus R2 divided by R1 into R2, which is equal to minus V0 by R2. Here we need to substitute the value of V3, which is we got in terms of V2 in the equation. So that will be modified as V1 by R1 minus R2 by R1 plus R2 into R1 plus R2 divided by R1 into R2 into V1 equal to minus V0 by R2. So after simplification, we will get the equation in terms of V1 and V2. So which will be V2 minus V2 by R1 minus V1 by R1 equal to minus V0 by R2. So after simplifying this equation, we will move on to the equation of V0 by R2 equal to V1 by R1 minus V2 by R1. From this again, you can take it R1 outside. It will be equal to V0 by R2 equal to 1 by R1 V1 minus V2. So the V0 equal to R2 by R1 into V1 minus V2. If we consider both your inputs resistance R1 and R2 equal, then your V0 will be equal to V1 minus V2.